afternoon, my name is Juan Espinosa and I'll be presenting about the Lisa Pathfinder. First of all, gravity. Gravity is known as one of the four fundamental forces in the universe, as well as electromagnetism, the weak and the strong nuclear forces. Gravity has always been a puzzle to scientists and scholars since it was first presented to the scientific community. The Greek philosopher Aristotle sustained that all objects tend to be attracted to the universe, to the center of the universe. Now, there has been many different theories about what gravity really is. The Greek philosopher Aristotle sustained that all objects tend to be attracted to the center of the universe. Ptolemy argued that since all bodies fall to the center of the universe, the Earth must be fixated at the center. Otherwise, falling objects will not fall to the Earth. Copernicus proposed that Earth and the other planets revolve around the Sun, or what is known as the heliocentric theory of the universe. Now, gravitational wavelengths. The concept of gravitational wavelengths was first introduced by Henry Poincaré in 1905. Einstein predicted that violent events such as the collision of two black holes create ripples in space known as gravitational wavelengths. These ripples he explained, are similar to when you drop a rock into the lake, and the waves that it creates are similar to these gravitational wavelengths. Now, gravitational waves are disturbances in the curvature of space-time. They propagate as waves outward from their source at the speed of light. Gravitational waves transport energy as gravitational radiation, which is a form of radiant energy similar to electromagnetic radiation. Now, do these wavelengths affect us? The answer is no. Gravitational waves will pass through us almost completely unnoticed. These ripples in space-time carry more energy than any other cataclysmic event. The interactions are so weak that they barely affect us. When these ripples happen in time and space itself are stretched, causing a slight wobble. Since gravitational waves warp both space and time, atomic clocks could be affected by these waves, showing different times after the waves have passed. So, how do we know that these wavelengths exist? These wavelengths were first detected by scientists in 2015 by the LIGO-Virgo collaborations. Sorry about that. Scientists were able to detect these wavelengths by using an instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory. These wavelengths were caused by a collision of two black holes that collided about 1.3 billion years ago. The confirmation of the gravitational wavelengths was a huge event in the scientific community because it proved that the theory of Einstein was right, and it also introduced new ways to study the universe. Now, how are these detected? As I mentioned before, scientists use the instrument called LIGO. This instrument searches for any distortion in space-time that will point to the crossing of this type of wavelengths. It works by it basically extends two arms that are each more than 2 miles long. Since these wavelengths compress and stretch everything on their path, the wave will cause the arms to slightly change in length. The laser beams reflect back and forth off the mirrors, coming back to converge at the crux of each of the arms, which causes them to cancel each other out, which causes the beams to travel different distances. Now, the Lisa Pathfinder. The Lisa Pathfinder is a spacecraft designed to prepare the path to understand and detect gravitational wavelengths. This spacecraft was launched first on December 3rd, 2015. This spacecraft goal was to stay still, as motionless as possible, which will allow scientists to test new types of wavelengths, new types of technologies to understand these gravitational wavelengths. The main goal for this mission was to show in space environment that free-falling bodies follow the concept of geodesics. These wavelengths will greatly improve the current knowledge of general relativity, which is the main theory of Einstein. It will also permit scientists to detect the repercussions of astronomical events which are known to have insignificant effect in our universe. So basically all the events that we don't normally notice in the universe. Now, what is the purpose for this spacecraft? Its goal was to stay as steady as possible in order to test new technologies. It actually exceeded the ESA's expectation, which is the European Space Agency, paving the way for the gravitational wave observatories in space. It plans to follow up a mission which will be called LISA in 2034, and this this spacecraft had a main science spacecraft and a propulsion module. And the propulsion module was used to boost the LISA Pathfinder's orbit and to send it to the Lagrange point L1, which is one of the LIGO observatories. So the technologies that were tested by the LISA Pathfinder. The LISA Pathfinder was testing in flight the concept of low frequency gravitational wave detection. It has put two test masses in near perfect gravitational freefall and is controlling measuring their motion with unprecedented accuracy. The spacecraft had a main scientist spacecraft and a propulsion module. The propulsion module was used to boost the LISA Pathfinder's orbit and to send it into the Lagrange point L1. The key technology to this mission was the LISA Technology Packager, the LTP. So in conclusion, this spacecraft, the LISA Pathfinder, is paving the way for many future many missions to test the effects that these wavelengths have in our universe. And it's using the latest technology to minimize the extra forces on test masses. So this LISA Pathfinder is an ESA mission, which is the European Space Agency, and also has a NASA payload. So they're collaborating to create new ways to understand the universe better. And those are my references. Thank you for your time, and